what a square root is and even what x squared or a parabola, why it looks the way it does, and how to use the graph to even understand the actual shape of a square a little bit better. Square root is referring to an actual square. What we had mentioned, the idea was if you have bricks, these are like numbers, 1, 2, 3, 4, 5 bricks. Then we consider rows of bricks. We don't know how many are in each row. It could be a few, it could be many, it always changes. That's what we call x. When we're dealing with x squared, we're talking about a length and a width. And so it's asking how many squares there are in this little squares there are in this square, considering there's an equal amount on each side. That's what a square does. It has equal sides or congruent sides. So if it was a 10 by 10, we would know that 10 times 10 is 100. So there would be 100 little squares when you had a 10 by 10. We could continue this into cubed. Cube's talking about an actual three-dimensional cube. And so it would be asking how many little cubes would fit into a larger cube. And then we get into a higher level, x to the fourth, and we could not draw this. In another video I had quickly shown, it looks like this. This is called a tesseract. And this is a visual representation. It's really not 4D, but it's kind of an example of what we would think a four-dimensional shape looks like using a 3D shape on a two-dimensional computer screen. So technically it's not 4D, but I had mentioned in another video, we can use these and we can see the progression pretty easily using a line, and starting with a point. So a point has no dimensions, it's pointing at something. The next level would be a line. That's what we would consider like x. So a line is what we call a one-dimensional figure, and it's using how much of the previous, so it's using 2 points. The next level would be a length and a width, and that would create a square or a rectangle. This would be considered a two-dimensional shape. So this has a length, but this one has a length and a width. And when we consider what's happening is we're adding right angles to it. So the next, we can ask ourselves in this next shape, how many of the previous did we use? We use 4 lines to make a square. So we can use these patterns, 3D. 3D is going to need to use 6 of the previous, so 6 squares. And that's what you have when you have a three-dimensional shape or a cube. And the cube itself, you consider, we started with the one before it and we made right angles and we connected them. So we are adding basically right angles to the previous shape. And the reason there are 6 of them is there's the front, the back, the left, the right, and then the top of the box and the bottom of the box. So really there are, if you take a box and count it, there are 4 sides around it, 1 on top, 1 on the bottom, total of 6. So the idea in a 4-dimensional shape is it would be made of 8 cubes put together, and those 8 cubes would be kind of like at a right angle for each of the vertex. So it's kind of imagining right angles at every vertex, but it's going to be made of cubes connecting to one another. Once again, it's something to explore on your own. Is a 4-dimensional idea called the Tesseract. In physics, we consider 4 dimensions the 3-dimensional, what we have in human life. We have matter and things that you can feel and touch, like a table or a car or a person. And the 4th dimension they consider time. So really we would consider this shape 5th dimension if we included time. So the idea we want to focus on here is a square. So the idea we had mentioned in the previous video is these are what rows are x, squares are actually x squared, cubes are actually x cubed. So the reason for the name is because we're talking about those things. A square, x squared, is referring to the dimensions of a square. So let's take a quick look at that. It's really good if you have a young person at home and you give them little tiles, little squares to work with. You say, okay, here's a square. The sides are even. How many squares do we need to put together to make the next size square that would make a perfect square shape? And so this one's a 1 by 1, and it would make one square. So they might try one, they might add another one to it, and you'd say, no, that's a rectangle. Okay, they add a third one. Nope, it's not a square, and then we'd add a fourth one. So a 2 by 2 gives us 2 rows and 2 columns, or 4 total bricks. And we can continue this. They could play around with it, find the 4, maybe add another couple to it. Nope, that's a rectangle, add a third one. Oh, okay, now we have a 3 by 3. And we're using a total of 9 bricks. So these are what we consider in algebra perfect squares. Perfect squares will make a perfect square without chopping little pieces of bricks up. So we can continue 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5 by 5, and most of us know these. A 1 by 1 square, or 1 squared, is 1. A 2 by 2, or 2 squared, is 4 bricks. 3 by 3, or 3 squared, is 9 bricks. 4 by 4, or 4 squared, is 16, and a 5 by 5 would make 25 little pieces because you'd have 5 rows of 5. So when we understand that a square is talking about these actual shapes, it helps us to realize we're working with actual physical things. So what happens when we don't have a perfect square? So what about if I have 3 bricks? So let me take another view that has a slightly larger graph. So let's say I have 5 bricks. Well, that would mean I have a 2 by 2 with 1 left over. So I want to ask us, what is the square root of 5? Well, what does that mean? Well, let's talk about, before we get into that, what was the square root of 4? So what we're saying when we say the square root of 4 is that there are 4 little bricks. Square root of 4. Well, what is the root of one side? And so we know it's a 2 by 2. 2 by 2, or 2 times 2 makes 4. So if we have 4 bricks, we want to rearrange them into a square. We know it's going to be a 2 by 2. So when we're doing square roots, we break it by factors. We group them into 2's. 2 times 2. And the reason we only take one of those numbers to get our square root is because here are the 2 sides at 2 by 2. We're asking for what is the root of one of those sides, so we only use one of them. So when we ask for the square root of something, we're asking for what is the one side of that square when the inside is whatever number. So let's say the square root of 25. What is the root of one side? Well, it would be a 5 by 5. So a 5 by 5 will make 25 little bricks in the middle here. And we know the square root of 25 is 5. One of the sides is 5. So that's what the root is talking about. So what happens when we don't have a perfect even root? Well, I have 4 plus 1. Well, the idea is the square root sign is sort of like saying chop them up into perfect squares. Chop them and rearrange them. So I'm going to have to chop this into pieces. And maybe I'll put a piece here, and a piece here, and a piece here, and a piece here. And then I'm going to need to fill in that little spot there as well. So now I have a perfect square because the sides need to be the same. So I know that I used 2 by 2. I have 2. But I also had to chop it. So when we click the square root sign in our calculator, we're actually taking and chopping that extra piece up. So it's 2.23. So each of these sides would contain 0.2 of the one we chopped up. So we can even estimate square roots. So let's say you have the square root of 10. Well, we know 3 squared is 9. 4 squared would be 16. So we know it's going to be a little bit more than 3. So here are a 3 by 3. There are 9 squares, and there's one more left over. So I know it's going to be a 3 and another 3. And I would chop it up, and I would put a piece here, 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 and then here, and continue to have a perfect square. So if I use my calculator, I have 3.16. So one thing to consider is the nature of a square root. A square root of a non-perfect square, looking at the calculator again, it goes on forever. So this is a great, even the first 2 or even 3, they're great approximations. So we can chop up these pieces into 3.162. But the math behind it actually goes forever. So this number would continue and go on infinitely. So we can't really accurately, realistically cut it into those perfect pieces. So it'd be an imperfect square. The interesting thing about imperfect or about square roots repeating forever is that even though you can't even write out the entire number, you couldn't ever get to infinity, you could still draw them. So for example, when you have a 1 by 1 square, let's pretend this is 1 by 1, when you connect the diagonals we learned in a 45, 45, 90, we get square root of 2. So when we get the square root of 2, we know it's going to be a 1 by 1, and there's going to be a little bit left over. So it's 1.414213562373095, and then it keeps going forever. So this number, this shape, is cutting an amount that will never be a perfect amount you can really cut. So if you're talking about an actual cupcake, just realistically, the idea of cutting it into a square root or a decimal that repeats forever is really difficult to do. But again, we can draw it and we can cut it into different pieces. So on the one hand, we couldn't write this repeating, this decimal that goes on forever. We could never find the end of it, but we could actually find how to cut it. And sometimes we can do that in math, where you can represent something as a symbol, but you can't really cut it, or manipulate it in real life, and vice versa, kind of like x to the 4th. X to the 4th, we couldn't really draw it yet. We don't know what a 4th dimensional shape looks like, but we know it's x squared times x squared, so we can manipulate it or move things around and work with it in different ways. So let's talk about building a pyramid. If each square is a brick, or each little square is a brick, when we put them together we have larger and larger squares that we can make. So the idea of a pyramid would look like this, and the base of it would be a square. So if we were to cut each layer, have a layer here, a layer here, a layer here, a layer here, and look down on it, the top one right here would be this square. Then the next one would be a 2 by 2, and then a 3 by 3, and then a 4 by 4. And we would continue in that pattern until we got to the bottom, and the squares would be getting bigger and bigger and bigger. So when you see something asking you for a square root, just keep in mind you're dealing with an actual square. So if I said the square root of 9, I know it's 3 by 3. But when it's 10, I know I'm going to have a little bit left over, because I have to take that extra brick and put it around and make a perfect square. So another thing to consider when looking at squares is the graph of a square. So the reason that a graph of a square makes something called a parabola, in that curving shape, is because we're essentially going to be asking for each side of this type of square, how many squares will be in the middle? Let me show you what I mean. So if this is a 1 by 1, we have x squared. So when x is 1, how many bricks are we using? Well, the answer of y is how many bricks total is 1. When we plug in 2 squared, 2 times 2 is 4 bricks we would be using. 3 squared would be 9 bricks. A 4 by 4 square would be 16 bricks. So when we graph this, 1 is 1, 2 would be 4, 3 would be 5, 6, 7, 8, 9, 4 would be 10, 11, 12, 13, 14, 15, 16. So the graph will start at 0 and begin to curve and make what we call a parabola. Now if we're using actual bricks for building, we wouldn't have negative bricks. But in money, you can have a negative amount in your bank. There are practical reasons to use negative. So negative 1 times negative 1 is also positive 1. Negative 2 times negative 2 is still positive 4, because a negative times a negative becomes positive. Negative 3 times negative 3 is 9. So we see the same image reflected over when it's negative. So what we're really saying here is how many bricks are on each side, and here would be how many total bricks. And so we could very quickly see, okay, I wanted to find a 1, 2, 3, 4. A 4 by 4 brick would make 16. I can quickly and accurately, like a times table, find how many total bricks I would need. Let's say I went to 10. Well, it would be up here, it would be 100. A 10 by 10 brick would be 100. The 10 and 10 are the roots of the sides. So another thing to keep in mind or consider is when we're solving, it's the same thing we get visually when we graph. We learned that x squared equals 16. And in algebra, we square root both sides. And we say x is 4 and can also be negative 4. Because 4 times 4 is 16. Negative 4 times negative 4 is 16. So if I take that equation and I want to move the 16 over, subtract 16, subtract 16. So now I have x squared take away 16 equals 0. I can graph this. I can replace the 0 with y and graph this parabola. So what I want us to consider is when we graph this parabola, our roots, or where it's going through the x-axis, are going to be 4 and negative 4. So when we're graphing, we're still talking about squares and square roots. So let's take a look at it. Here's a free graphing calculator. It's a GeoGebra. X squared minus 16. And so what it's really saying is if you have a square of 16, the roots would be a 4 by 4 or a negative 4 by negative 4. And if we change it to plus, it would go up 16, and we would have something called negative roots. And the reason for that, I mean, we may not have covered it yet, but in algebra we do mention negative square roots. I just change it to x squared plus 16. So when I subtract 16 on both sides to solve without graphing, I'm going to have negative 16. When I square root it, I'm going to end up with square root of 16 and square root of negative 1. We can separate them. So we're going to have positive negative 4, and the negative square root we learned is the letter I, or imaginary numbers. Imaginary numbers are called imaginary, but they're really, when they first created them or talked about them in the 1800s, they called them lateral. They are up there, off to the side on a graph. They just don't show up. And so there's another way of graphing we learned later in higher math, where we'll have normal numbers here, like 5, and then imaginary numbers here, 3, 4, 5, imaginary, 5i. And so we can graph 5 plus 3i just means go to the right 5 and go up 3 imaginary numbers. And so our parabola graph, when we're using an imaginary number, it goes up here. And there are no roots that go through the x-axis. The roots would be what we call imaginary, and it would be lateral or off to the side or even up in the air. There are some good videos if you just Google what are imaginary numbers or look it up on YouTube. So a square root is talking about an actual square in that shape. And the same concept applies for cubes and cubed roots. It's talking about cubes and what each side would be in a cube. So a cube is a square, like the bottom here, but it also goes up and has another dimension. So the cube root of 1, because there's a length and a width and a height, we have 3 dimensions. So what it's saying, the cube root of 1, is if there's 1 cube, well, the dimensions would be 1 times 1 times 1, or 1. If I had a cube with dimensions 2, 2, and 2, my base, or the bottom, would be 2 times 2, or 4, and it would go up 2 rows. So 4 times 2 is 8. So they would say, what's the cubed root of 8? If I had 8 little boxes in here, or cubes, I'd know the dimensions would be 2. So the way we teach this is to factor it, 2 times 2 times 2, and we say for every 3, we take 1 out. And that's because there are 3 dimensions. The same way we say when there's x square root, the square root of 25 is 5 times 5. There's an invisible 2 we don't write. It's saying we want, for every 2, we take 1 out. And the reason for that, again, is because it's saying the root of the 2 sides are 5 times 5. One square root is asking for one of the sides. So we don't look at both of them. We take the 2 and turn them into 1. So there's a lot more to cover and explain, but it's helpful to understand in some ways that algebra and geometry are very applicable and useful in real life situations. We used it all the time when we were building things like pyramids and monasteries and cathedrals, and we use these same concepts in finance, science, and in other ways as well. But I'd like you guys to just consider that a square root is talking about an actual square. X is basically a row. X to the third is talking, or x cubed, talking about actual 3-dimensional cubes. Hopefully that helps open your mind a bit, because some of this I really didn't understand until later in math. So take care. Have a good day.